Oh yeah, I saw that. So, okay. Yeah, there are no 64 code makers. That's not how it works. So, first of all, I'd like to test one thing. So, can you see? No, you cannot see. Oh, you can see this. Wow, okay. So that's going to be handy in case I need to show you some of that. No, there's no 69 code makers too. That's not how it works. So minicard, was this all minicard? SMC4 play. Was it 2 months ago that I worked on that? Yeah, okay, so that's why I'm doing live streams now. To kind of try to motivate to do this. Oh my god, I have so much data that I have to deal with. Colors. Yeah, I even had a color standard for like both in Scrap Mechanic and in the... Yeah, this is actually mainly for in Scrap Mechanic. So these are all the registers that the computer has. There's like 6 registers that you're supposed to deal with in the program. There's a hidden register that's kind of only for the sub-instructions. The 16-bit bus entries, we already did those. So these are, I'm just going to mark them green in here. I've already done them, done. And there's also some flags that have to do with the ALU. So today, I think we're going to be building this here. It's essentially... it's essentially going to be one... We're going to be building a 8-bit register that's going to be good for the computer. And we are going to be making 7 copies of it and connecting it all to one bus. So let's get going. So let's create some space already. Or just find a register. So SMC3 register that I was going to be using. But I want it to be flat. So I can stack 7 of them up compactly. A 4-bit register. Nope. Nope. Then we have a 8-bit counter register. So the Q... Over here, the Q register. That can count. So we will need it for that. That's mainly for handy for counting loops. Oh yeah, yes, I made this. That's true. So I made this one here, and it's a counter register. Oh yeah, that's true. So I think I made that for somewhere in here. Is this a counter register? Yeah, that's a counter register. This is for 1 ticks. Like that. And that's the same thing, right? Except with a concrete layer below, yeah. And some extra I/O logic. Oh, so this is one that you can also write to, of course. Okay, so we already made this register. Interesting, very interesting. So this is the counter register we're going to be using. And essentially all of this here is just for the counter. So we don't need that. Yeah, this is my own triple extra memory. The glitch-free extra memory. 8-bit, maybe that also gets some flat 8-bit counter. Memory, 8-bit manual. Oh, that's the flip-flops, I hate them. They need 3 tick pulses. SMC3 register. Nope. So I'll have to make a register. Why do I keep needing to make registers? I'm like, why have I never apparently created a register and just saved it to be able to use it forever? So usually the way I make a register is I just make 1 bit and then copy it over 8 times. Let's do that over here. Actually, I did this wrong. We need some concrete below so I can place stuff on. So first thing we need is the AND gate as an output. Then 3 XOR gates. This is going to be the actual memory. Then we need some logic to be able to reset it. So essentially, if the gate is on, and we get a reset signal, reset the gates, and we have to put in another gate just to make sure that you don't get a, because you can't like connect the gate that we're getting this from directly back to that's not how it works. So you have to do it from another gate, which is going to paint black. And then we have the data input gate. And essentially, that's it. Actually, you could make this an OR gate and have both of them go in there. Yeah. So the idea is that you could have a button. You can have, it has two functions. It has a reset function and a write function, and then that there would be the data. If you want to write, you have to do both reset and the toggle. So essentially what it will do is it will at the same time, because you can do that, actually it needs to be an XOR, not an OR. So at the same time, it's going to reset it and toggle it if it's turned on. So it'll be turned off first and then turned on again. But because it's go through this XOR gate, it's actually going to be, if it's resetting and setting at the same time, it'll just stay on. So let's just test it. So if you reset it, nothing happens. If you try to set it to 0, nothing happens. Wait, why does this... Oh, of course, it's an AND gate, so I have to go... But that's... Okay, we don't need the reset function. That's useless now. Okay, so we can turn it on, and we can turn it off. Nice. So I think I'm just going to make the output white, and the input will be blue. And the trigger, pulse in will be cyan, but we're going to be doing that via a main gate. So I'm just going to make this one will be made black later when we have 8 of them in a row. So now becomes the fun part. So you can save this as unnamed. Then I'm going to make 8 copies. 7. No, no. Oh my god, I pressed the upload button. Next up, we need to add a gate that actually... So we need 2 things. So we need an enable input for the enable output, and a enable input for the data write. So because the output isn't a pulse, I'm just gonna make it lime, and because the input is a pulse, it's going to be cyan. And then becomes the boring part. We have to make 16 connections between the cyan and the blue and the red. So what I'm amazed by is that the normal register is like no bigger or smaller than the counter register. Oh wait, it's in the wrong orientation. Still, it's only 1 block. What? Did I do something weird? Is this not what I think it is? I can just write stuff, right? Yeah. Oh, there's no output disable. So that's one gate that's... But then how do you even... I think I've done something that's more clever than I am smart now. But yeah, I do have to add a output enable to this. Let me quickly do that. Wait a second. I put the triggers on the wrong side. You know what, we might spin up Brent Batch's blueprint tool for that. Okay, good. And then we have a button for that, of course. Next up, I'm gonna quickly blueprint edit this. So save as unnamed. Now, I am going to open up Advanced Blueprint Tool. Oh god. Invalid digital signature. Unable to check for updates, yes. Yeah, it's getting kind of outdated, which is very sad. Let's open a blueprint on named load. What? Okay. Yeah, that should be better. Save override. Okay. See, fixed. Don't need you actually. Let's just check that he didn't do anything weird with the connections. Let's just because I do trust the blueprint test. Oh, actually, we can also rotate these gates around. Let's do that. Apply render. I think that works. Save override. Resume game. So this one is incorrect now. Actually, just keep it as a backup. Oh wow, it worked. I'm a master blueprint editor now. Let's now check if the connections actually still work already. Oh, of course it helps if you connect the button. And connect the... Oh wait, I did connect the switches. Uh-oh, that's no good. That doesn't seem to be working the way it should. Oh wait, no, it is. I'm just a dum-dum. Yeah, okay, this is working fine. Yeah, okay. So now we have the finalized versions of registers. Woohoo! Why do I want to rotate it? Because it looks nice. This AND gate is pointing into the things it's controlling. Same for this thing. And these are controlling these XOR gates. So really these should be rotated around as well, but I don't bother at this point. But it's just to differentiate between the bulk inputs and the things on the side that control the bulk inputs. Why would I need to debug a register? Well, if anything goes wrong in the computer, like 9 out of 10 times, it's at some point going to encounter a register, which doesn't just mean that, there's a chance that it's inside the register, but also that the register might give you information about what else was going wrong in the computer that to cause the error. So being able to easily see how a register works and to be able to get some debugging connections in, that's going to be helping a lot. So I need 6 copies of these and 1 of this one. So I want to install these all in a kind of rack. So we have 7, 3, 4, 5, 6, 7. Let's now make 7 of these normal ones. 6. So now I have all the parts I need, and let's now look at how we are going to be assembling all of it. So if you look at the registers we have, I think I'm just going to put the A, B, H, L, D, Q, and I in that order in there, so I don't confuse myself all the time. So Q is a special counter register. The R register is indivisible, but to the computer architecture that doesn't really mean anything. It just means that this one here isn't just going to be directly involved in one of the... Like you won't find a instruction that writes this to register A, because that's not useful. Here, would you look at that? It is too much. I think this is alright. Okay, so I can emulate the PC using my brain. That's simpler than making it in scrap mechanic. Well, I'm too lazy to emulate it in my brain. That's a real reason I'm doing all this. Then we have the counter. So trigger for input, increment, decrement, some output and output enable. Oh, it's gonna look weird, but that's alright. And the instruction register. Okay, so now we have this very nice compact register module that will store all our 7 registers. It's going to be important. So yeah, we just did the register module. This is the entire thing. Okay, so that's going to be the end of the video.